Evening. This is the third in our series of panels that relate to the Green Architecture exhibition. The first two talks were on sustainable homes, sustainable communities, and this evening, sustainable campuses. Meg Vickery, our guest curator, will introduce the speakers. Before I turn this over to Meg, I want to mention that this is our exhibition brochure produced by the Gazette, Daily Hampshire Gazette. Please pick one up before you leave. It gives Meg's wonderful curatorial essay. There's an interview with Meg, and it also talks about our upcoming panels. The next one will be April 15th on sustainable gardens. There will be a home tour, garden tour. Check our website, check the brochure, and stay with us. We're also videotaping tonight's talk. We've videotaped the two previous panels, so if you missed them, you're welcome to check back with us. We will soon, I think, have them on our website, but we'll have a kind of audiovisual connection to this material. So thank you for coming, and I'm going to turn this over to Meg, the wonderful heart, soul, and mind behind the whole project.
Thank you, and thank you everyone for coming tonight. Just before I forget, if you're here and you want AIA, Western Mass AIA credits, you want to see Lauren Starr, right? You didn't even have to remind me this time. So anyway, as you know, the talks tonight focus on sustainable architecture on college campuses. And as we move towards a sustainable future, our colleges and universities are playing a vital role in educating the next generation. Students need to learn about the term sustainability and what it means in a variety of academic disciplines, while simultaneously understanding their own personal role and responsibilities within these global issues. As you'll see, our speakers tonight represent a wide range of approaches towards educating students about these issues relating to sustainability and the built environment. Our first speaker tonight is Todd Holland. Todd is the energy manager for Amherst, Mount Holyoke, and Smith colleges. The shared position was established to furnish the schools with specialized expertise needed to identify, analyze, prioritize, and implement energy conservation projects and programs. Projects implemented run the gamut from replacing light bulbs to building new combined heat and power cogeneration plants. As energy manager, Todd works to establish collaborative committees among the consortium members to promote energy conservation and to avoid duplication of efforts from campus to campus. Todd has been in the position for just over 5 years and came to the colleges with a background in engineering consulting, energy services, and aerospace industries. He's a graduate of the University of Connecticut and a licensed professional engineer in 6 states. Todd?
Good evening. It's nice to see so many people here. I'm going to have kind of a funny presentation tonight in that I'm going to bounce back and forth between a couple different types of media. So we'll start with the PowerPoint, which I've got some really awful slides for you. First off, the bit of a misnomer. I work for the 5 college consortium, but I actually only serve 3 colleges. So I work for Amherst, Mount Holyoke, and Smith. So I had one of my first introductions to the custodial staff at Amherst College was a big giant room, amphitheater, full of all the custodians, and the head custodian at Amherst College is actually a friend of a family friend. And about 3/4 of the way back, he raises his hand. He says, let me get this straight, Todd. You work for 5 colleges, but you only really work for 3 of them, so doesn't that mean you only ought to be making 60% of what you're making? So, thanks, George. But I'm going to try and give you a brief overview and just where the energy comes from, what we're using it for in the campuses, why that's important, which is really the greenhouse gas emissions, what we're doing about it. One of the things is green buildings. I'll give you a real quick overview on 3 of the green buildings and what's changed in the 5 or so years that I've been doing this. Isn't this a lovely graph? This is the Department of Energy. This is our tax dollars at work. I absolutely love this thing. We could stare at this for hours, and I do. But what this shows you is where the energy is coming from over here. These are all the various energy sources: coal, natural gas, crude oil, Natural gas liquids. Nuclear is that little arrow there. Renewable energy is that little teeny thing right there. And this is petroleum down here. And so this is domestic production, 70% of the input to the process, and that's imports. And then it shows where it's going. Residential, commercial, industrial, transportation. So that kind of shows you what we're doing with the energy. And those four sectors are roughly equal. Industry is the biggest. We still actually make things in the United States, believe it or not. But the important thing here is if you color the input, that brown part of the input is what is fossil fuel. So that's kind of sobering. Most of the input to our energy process, which does everything we want to do, live, work, make, move, is fossil fuels. What do we use the energy for? So if we take that right side of the graph, which is the output of our energy use in this country, there's those four almost equal sectors: residential, commercial, transportation, industrial. But most of those are buildings. Residential, that's just about all buildings, right? That's your homes. Commercial, that's all buildings. That's where we work. Industrial, a lot of that energy is maintaining the building that the stuff is being made in. And then transportation is no buildings, because most of our buildings don't move. So when you really look at it, most of our energy consumption, 48% of it, is in our buildings. So if we want to do something about energy, we want to do something about greenhouse gases, we have to do something about buildings. And I'm sure you guys are here, so you already know that. This is what happens to the energy. Most of the energy that we use, you could see from that left side of that awful, is fossil fuels, hydrocarbons. So what we really want, and here's a quick chemistry lesson, I hope there are no chemistry professors in here. Most of that energy comes in the form of hydrocarbons. We want the hydrogen. The hydrogen is what gives us the energy off it. We're left with the carbon. The carbon combines with the oxygen in the atmosphere and makes CO2, which is a greenhouse gas. This is our greenhouse gas footprint at Smith College. 31,000 metric tons of CO2 a year. It's almost impossible to visualize that, but let's just say 31,000 tons of a clear, tasteless, odorless gas is a lot. It's a big thing. But most of it is from burning fuel on campus to heat the buildings. 54% of it. 29% of it is created by the plants we buy our electricity from. Everything else, all the little mowers and stuff and trucks driving around campus, 1%. Agriculture, which means the greenhouse gases from the stuff we use to kill weeds and keep the grass green, is less than 1%. Escaping refrigerants and other chemicals is less than 1%. All the people who come to Smith College from all the various towns in the valley are 2%. Our professors, which jet all over the world going to conferences in Tahiti and all this other stuff, recruiting students from all over the world, that's 10%. That's big. You know, that's a lot of jet fuel we buy. But most of it is the buildings. So to do something about our greenhouse gas footprint, and Smith College has committed to get rid of it all, to go carbon neutral. They have signed the American College and University President's Climate Commitment, which is to go carbon neutral. You got to do something about your buildings primarily. So one of the things we do is green buildings. And so I'm going to switch things here and show you a quick movie, because the students I get to work with are far more talented than I am. I'm Todd Holland, the energy manager, and we did some work in this building, the new residence hall. I'd like to talk about the solar hot water system and the energy-saving shower heads. This is a LEED Gold certified, which the highest standard is platinum. Originally, the building was supposed to be silver certified, but we did so well during the design process that we got enough points for gold. One of the biggest energy users in the building is hot water, and most of the hot water in the building is used for showers. A good portion of the hot water in the building is made by a solar hot water system. There's 24 panels on the roof, and we can see its performance over time. And on this day, this is the line. It was a sunny day a few days ago when we made about a little more than a third, almost a half. Almost a half. Gives even more energy than the solar hot shower heads. And this little shower head uses 1/3 less water than a regular shower head. It mixes the water with a little stream of air, and then that makes the water come out very fast. So you get less water, but it comes out at a very high rate of speed, so you get a nice invigorating shower, and people like them. Okay. I did all my own stunts. And you notice the camera work was nice enough not to focus on my helmet head after riding my bike to work on that summer day. But that's our newest residence hall at Mount Holyoke, which hasn't built a residence hall for years and years and years. But the illustration there, and it got a little garbled, is we have a solar hot water system on the building. That building at Mount Holyoke was our third LEED project. And the first LEED building was a science center. And as some of us will talk about, a science building is an extremely heavy user of energy. And that building, in the category of energy and environment, got 2 LEED points, which were the prerequisites, and no more. So we learned a little bit from that and went after the energy hard in this building with the residence hall. And it triggered a renovation of the Science Center, actually. And we installed some of the features in the science building that were originally value engineered out. The next was a campus center, an adaptive reuse of an existing structure. And that was also LEED certified. But the comment that we got a lot on these 2 buildings is, what's so green about it? Where's the solar panels? And we could point to the marmoleum and all these other lovely finishes and certified wood and the recycling rates during the project. But people wanted to see a crowning feature on the building that was green, so we put solar panels on it. So 24 solar panels on a 172-bed dormitory. Now, does anybody have solar hot water at home? How many panels you got in your house, Tom? 3. How many kids you have?
2.
Yeah, so Tom has a ratio of 3 to 5 panels to people. 24 solar panels, 172 students. So we're not making all the hot water with the solar hot water system. We're making about 25% of it. But that solar hot water system cost us maybe $300,000. The shower heads save 30 to 40% of the water in the building. They cost $3,000. So the green feature there really is the shower heads. And I'd like to thank my daughter for helping, suffering through the trials that we had to go through. We tested a whole bunch of shower heads. But back to the, and I'll show you something else that didn't work too well on that building is in the movie we have this little thing here, which is our green touch screen. Now if you go in the lobby of that building, you see that nice touch screen, which actually doesn't flicker like that. That's part of the video effect. But this is something that explains exactly all about the LEED building. And you can go through and you can pull up any of these tabs. We have an energy competition where we can compete floor to floor. It explains all about electricity, where the electricity comes from. You can read about the boiler plant, the boiler power. You can find out about the Mount Tom coal plant, see how much thorium that puts in the air here. Students don't use this thing. They don't care about it. I was really happy to write all this stuff, and I had a great time, but it really needs to be a little simpler. And the basic idea is that this was a dashboard that you could walk into the building and see how much energy we're using. You know, and so if we wanted to look at the solar hot water, we click on that tab, and this loads the screen that was shown in the video, and it shows that today and yesterday we had a lot of sun, right? It was a nice sunny day. Today, not so much. It was a little cloudier, but Wednesday we were making, you know, they were using this much hot water, but we made, you know, that much of it, which is really, really nice. And right now we're not making any, really. We got a little residual in there. But it also lets us find out some really interesting things, like dormitories in colleges don't really do much until like 10 o'clock at night. And this is every day, and that's every system. Students shower at 10 o'clock at night. They turn everything on 10 o'clock at night. That's when you really start cranking. This is kind of interesting. And that was my dream for this, that they'd want to go move the needle, right? But at Oberlin, they had an energy competition. They gave them the orb as the display device. They told them nothing. I tell students, you can go around here and find out how to change your light bulbs and put your computer to sleep and all this other stuff. They told them nothing. They figured out that one of the biggest electricity users in the dormitory was the clothes dryer. And so what did they start doing? They'd break into the dorm next door and do their laundry in the middle of the night over there. So this was a lesson learned, over-providing. And back to the PowerPoint. So, but the greenest building, I think, isn't building a new dorm. That's also kind of an ironic thing. Mount Holyoke really needed a new dorm. They didn't have any quote-unquote swing space. So if they wanted to renovate a building, they were forced to do it during the short summer months. And so every project renovating 150-year-old dorms was packed into a summer, and it had to be ready by September. So as major issues came up, major mechanical retrofits, asbestos abatements and the like, they needed a place that they could put students in and move them out for a whole year and spend a year fixing a building, which is something that Amherst College does. And this is another solar hot water project. You can see this is right on Route 9, right before the green in Amherst. And this was originally built in 1956, renovated a couple years ago, 44 beds, and it is 70,000 BTUs per square foot per year. So that is the thing that I'm trying to concentrate on. How much energy do these buildings use?
So that's the, renovated, gotcha.
Yep, so Tom can go on all the details, but there's foam insulation in the walls and a lot of insulation and air sealing that went on, new windows, new mechanical systems, substantial renovation of that, and we're a little bit higher than the average residence in Massachusetts. The average residence in Massachusetts uses about 67,000 BTUs per square foot per year. The big difference being that you don't cook any food. You don't cook food in this dorm. There's no kitchen. The one completed this summer did quite a bit better. That's not a real photo, right, Tom?
Nope.
Okay. Yeah, there's no red keg cups on the front line. That was opened in September. It's a little bit bigger, 73 beds, but look at that. That's kicked the energy use down to 41,000 BTUs per square foot per year. This is Mount Holyoke, and one thing really nice about Mount Holyoke, it came in really close to what the modeling said it would, which I was thrilled about. It was a brand new building, built from the ground up. It's a rather large dormitory, 172 beds. That is down to 36,000 BTUs per square foot per year. But again, none of these places have kitchens. But this is what you'd expect, right? If you took your house and took the kitchen out of the equation, that, you know, maybe you'd cut almost half the energy out. This is how the building would have looked if we just designed it to code, that most of the energy used per year would be space heating, which is also similar to what you find in your house in the Northeast. Lighting and electricity makes up a good chunk, and then the hot water for showers is that. What we got was 40% lower than code. That's pretty good, although I know Bruce and other people are making stuff that's 10% of code, you know, so this is good, but it's certainly not in the realm of what's possible. Again, solar panels on the roof, the kind of green necklace that everybody wows over, but the real showstopper there is the shower heads. Conway House, this was built in 2006. This is a small apartment complex for non-traditional age students at Smith who have families. So this is a real residence. It's an 11-unit residence, and there are people living in there, and they have a full kitchen. So this is a real residence house, and that's down 34,000 BTUs per square foot. This is a thermal vault. It's built with 12-inch SIP panels, which is a sheet of foam with plywood glued on either side. Really nice on this type of housing because the walls aren't hollow, so bugs and rodents have no place to hide from you. It's easy to seal tight, and it's really easy to hang a picture because it's plywood behind the sheetrock. You don't have to find a stud, which I'm notoriously poor at. So that's down 34,000 BTUs per square foot per year. And so just to go to some even more awful slides besides that first one, the DOE slide, I thought I'd make some really pathetic, never do this in PowerPoint. So what's been going on since 2004? I've been at this a little more than 4 years. Well, the CO2's gone up in the atmosphere 4%. I'm sorry. 4 years ago we were at 374 parts per million, now we're at 390. Electricity doubled in cost for the colleges, which was amazing. One of the things that amazed me is it didn't make my work twice as important. Fuel more than doubled and has since gone back, but back when I first started we were paying 79 cents a gallon for the ugly, dirty fuel oil we burn at the colleges. Can you imagine that? And now we're paying $1.33 a gallon. So electricity almost doubled, and fuel has gone up by more than 2/3. What else has happened? This is very interesting. Do not notice the difference between BTUs per square foot per year average on the campuses. One thing this tells you at 185,000 BTUs per square foot per year, that paying attention to the residences, which are well under 100, is probably not where the treasure is. Amherst College has dropped their BTUs per square foot 14, so for an 8% reduction. Mount Holyoke has dropped theirs a 6% reduction, and we're doing a lot more than just building green buildings or retrofitting the spaces we have. And Smith has taken a whopping 16% reduction in the BTUs per square foot per year. And what's that happened to the greenhouse gas emissions? Amherst College has reduced theirs by 28%, only spending money on things that make money. A lot of that is cogeneration. We're making electricity on campus now. And so instead of throwing away the heat like a power plant does, warms up the Connecticut River, we use the heat on campus. Mount Holyoke has reduced their greenhouse gas emissions 19%, and Smith has reduced it by 11%. So it's not all green buildings. Most of it is doing other things, finding where the power is being used, finding egregious waste of power, and retrofitting the buildings we have.
Thank you, Todd. That was great. How do we convince people to change the way they live? That's one of the big questions, I think. Our next speaker, as he gets his PowerPoint up and going, is Cahal Stevens. He's a former president and CEO of Einhorn Yaffe Prescott Architecture and Engineering, PC, a 350-person design firm with offices in New York, Boston, Washington. Serve on the firm's board of directors and as a consultant to the firm. He joined EYP in 1993 and worked for 3 years in the firm's Albany office, where he started the firm's practice in the design of buildings for science and technology, with a particular emphasis on undergraduate science. In 1996, he opened the firm's Boston office that has since grown to over 70 employees. He has led design teams for many large academic and other buildings, including over 20 major science buildings at colleges and universities throughout the country. He and his colleagues have been active participants in the national dialogue about the part buildings play in science teaching and learning through writing and speaking on the subject. In the early 90s, he served as a co-chair of the Architects for Social Responsibility in Boston, when that organization was an early advocate for sustainable design. He's been an advocate for sustainability within the firm and on all the projects he's led. He's recently completed the conversion of a 19th century cottage in Northwest Ireland into a net zero energy, net carbon neutral building. Oh, I love Northern Ireland. Anyway, he'll be presenting a paper on this project at the International Passive House Conference in Dresden, Germany in May of this year. He obtained his Bachelor of Architecture degree at University College Dublin, Ireland, and is a member of the AIA and the Royal Institute of Architects of Ireland, as well as being lead accredited professional. All right?
Okay. Thank you, Meg.
Sure.
What did I do? I blacked it out. There we go. You might wonder why I would start to talk about green buildings with a picture of Winston Churchill. But Winston Churchill, in 1943, when they were rebuilding the House of Parliament in London after the depredations of the Second World War, said something very important about buildings. First we shape our buildings, then they shape us. I think it's really a profound thing that we architects particularly should think about, the implications or the effect that the buildings they design have on people and everything people do in their lives. But 50 years later, Stuart Brand, the founder of the Whole Earth Catalogue and later the author of a book called How Buildings Learn, added to Churchill's wisdom with a nice added phrase. First we shape our buildings, then they shape us, then we shape them again ad infinitum. And I use this to start the talk because I want to talk about 4 buildings that we reshaped. And we reshaped them by not just renovating them, but also by adding to them. The first is a science building at Mount Holyoke. Second is a science building at Swarthmore College. The next at Hamilton College. And the last, not yet built, in Trinity University in Texas. And these all have something in common, although as you can see, they are very different buildings. They are all first of all, they're all reshaping of existing buildings with major insertions of new construction. Secondly, they're all between 100 and 200,000 square feet in size. Thirdly, they all have a green agenda, and it's a different green agenda in each case, and I'll talk a little bit about that. But most importantly, they are buildings for learning, buildings that are intended for the learning of science. And what does that mean? The learning of science and science itself has changed quite dramatically in the past 50 years since most of the original buildings were built. Most of them were built between 1930 and 1960. There was, of course, a big building boom in college campuses in the 50s and 60s after the Second World War. But science has changed in many ways. Firstly, science was considered in the mid-20th century as disciplinary: physics, chemistry, biology, psychology, and so on. Nowadays, all of the advances in science, or most of them I understand, are on the intersection of the disciplines. So interdisciplinary work is a vital part of modern science. Think of neuroscience, think of biochemistry, think indeed of environmental science. So these buildings are intended to bring the sciences together. Secondly, science is learned in a different way nowadays. Students learn not by doing what I did when I went to a lab in University College Dublin a long time ago in the 1960s, doing a prescribed experiment that was laid down by a professor. Nowadays, students learn by discovery learning. They are doing experiments themselves that they are thinking of, and they're imagining what the implications of what they're thinking of will do. They're learning by trying and by experimentation. They work in teams rather than individually, and often interdisciplinary teams. So creating places for people to work together is a very important part of science. Science has changed because the emphasis on safety is great now, and therefore the emphasis on ventilation of buildings, particularly chemistry buildings, where we're using, the science is about handling what are volatile organic compounds. So the building must be ventilated, and that's, as Todd said, they're great energy users, therefore the opportunities for saving are great. Finally, just as in every other aspect of our lives, information technology has a huge impact on the learning of science. And instrumentation has become very sophisticated and available to almost every institution, quite sophisticated instrumentation, scientific instrumentation, and of course all the obvious ways that information technology affects our life. So, I gave myself a challenge because I said I'm going to talk about 4 buildings in 15 minutes. Meg told me she was going to be forgiving about the time, but I think I owe it to her to speak fast, so I will continue to do so as much as I can. First, and one last thing, the program on all of these buildings is basically the same program. This is the basic program of an undergraduate science building. Teaching laboratories, research laboratories, offices, support, instrumentation, and classrooms, all tied together by perhaps the most important space in the building, which is the social space. And the design of that social space is just as important as the design of the laboratories or of the classrooms, because that's where the students learn from the faculty, learn informally, and do a lot of their work, as you will see. So, Mount Holyoke College Kincaid Hall was completed in 2003. I wish Todd had been around when we were working on it, because perhaps we wouldn't have had that value engineering that you mentioned earlier. But it was an interesting building because the green agenda was there driven from an unusual source. We had come to the college, we talked about green ideas, and they were listened and agreed it was a good idea, but they had a very limited budget and they were very nervous about spending it on things that weren't tangible and programmatic. But a donor came along and said, if this building can be LEED certified, I will give you a significant gift. Well, that helped us and helped the college make the building, certainly our first LEED certified building, and I think one of the early LEED certified buildings in the Pioneer Valley. Here's the floor plan, and I mentioned that it's a reforming of different, the site plan. It's reforming of several different buildings, 4 buildings that are all science buildings that were already there, and the new construction is this little bit in the middle. Although they were all adjoining one another, to get from Shattuck Hall to Carr Lab, you had to go down a stair, down a corridor, don't forget to turn right where the green door is, down another corridor, up the steps, round the back, and you get into the loading dock, and then you get into Carr Lab. Well, that's not a good way of encouraging interdisciplinary interaction. So one of the jobs of the new building was to link all these buildings together so they would become a single unified science center. And what we did when we went to Mount Holyoke, we said to them, you have a very limited budget. Let's build as small a building as we possibly can and spend as much money in retrofitting the existing building. And so the addition is 40,000 square feet, and the remaining space is well over 100,000 square feet. And we renovated most of that. The square, or the red rectangle encloses the new construction, which is primarily consisting of the atrium, the central space that ties the whole thing together. And a lot of the renovation money went into the chemistry laboratory here. This is the atrium, which is very tall and narrow because it had to link all levels of all the buildings. And Clap Hall that you can see through the window in the distance was 4 stories, so we wanted to link to all levels because we didn't want to leave anybody isolated from the central social space. The other lesson about this space was it needed to be active, very active all the time. It needed to link with all of the other activities that are going on in the building, so you can just barely see some windows looking into the chemistry building here, and all of the space on this side is activated, so you can always tell there's things going on, and it's a very important space, the heart of the science complex now. We also made some overt efforts to learn in the building. This is in the linoleum floor. We cut in the solar system, so it'll connection, a little bit of learning. And here we cut in a diagram of a neuron. Apparently this is a firing neuron, and there's a trailing nerve that runs all the way down the corridor past all the offices and labs. Again, it's sort of a diagram of science on the floor of the building. In the renovated chemistry building, we were short on space. The ceilings seemed very low, so we eliminated ceilings, hung ceilings in the lab. That served to give you a slightly better feeling of height. It also allowed you to, a practical thing, it allowed access to the ductwork and the conduits above. But it also helped students understand the amount of energy that was going into this building as they look up and they see these pipes, ducts, and wires, this huge amount of things happening to make the study of chemistry possible. Moving on to another science building at Swarthmore College, finished a year later. Here the green agenda came from the faculty, and from one particular faculty member who was an engineering faculty, wasn't actually part of the building, but he was the chair of the green team. And it was a very conscious decision from the beginning to make this a visibly green building. It started also with some disparate science buildings that were close to one another but not connected. The challenge was, how do you connect all of these buildings? Well, we did that by demolishing part of the DuPont Science Center that was not working and was inefficient, and by linking it all with in the reddish color, a sort of spread out, almost rambling building that served all the different science disciplines and connected them to one another, and also had a science commons, and again a social space analogous to the space at Mount Holyoke, the atrium at Mount Holyoke, in the center, in the kind of center of gravity of the space. Because you saw on the site plan there's lots of courtyards and ins and outs in the building, and that was very conscious because we were trying to connect the building to the outdoors, and no matter where you were in the building, you had a very strong connection with the outdoors. So there was an outdoor classroom, a number of these actually, and we also celebrated the natural rainwater coming down. Rather than by sending it in a pipe, we put it in a channel so you could see the water coming down, and then it would go into a cistern where it was used to recharge or to irrigate, I should say, the campus. And even in the internal classrooms, large, simple classrooms with large windows, so again, you had a connection with the outdoors. And most of all, in the science commons, it had windows on both sides, so again, strong connection with nature. But also a very important place, the sort of heart of the building. And in this place, we also had an energy monitoring system, and the faculty was insistent that this was not going to be a digital readout, but rather it was going to be dials, analog dials, so that you could understand the scale of what was happening. You weren't just reading numbers, but you were actually seeing the needle move up and down, and you could tell whether you're just moving 10% or whether you're moving that much. This also, I think, gives you an idea of, if you are going to have an energy monitoring system, what are the units you're going to measure, and how are you going to measure them, and how is it going to be effective enough that it will be useful. And I think my observation is, and this is not a scientific study by any means, that these kinds of things are useful if they are connected with some kind of a curriculum. If they're just in the lobby for people to see them, people look at them and yes, they're interesting, but I'm not sure that they really react or respond or they really are effective. But we can have a discussion about that afterwards, and perhaps other members of the panel have some ideas about this. But this was an interesting version of an energy monitoring system that is, I think, fairly unique. Another thing, I mentioned that we had lots of glass because there were strong connections with the outside, a place where there was very much a learning component, and an interesting environmental problem that's, I think, good for us architects to remember is that one of the major causes of bird deaths in the Western world is healthy birds flying into windows. And it has a huge impact on the avian population of the Western world. Well, we knew this, and we knew that in this building we were having a lot of glass, so we consulted with Dr. Daniel Clem of Muhlenberg College, who's an expert in this subject, and by the way, I have, if anyone's interested afterwards, I have some references of some of his writings that are very useful. And he guided us in the design of the windows. And here you see the window of the Science Commons, and you can see that at the upper parts of the windows, there's a grey tint on the windows. We used a frit behind, which is a perforated metal coating behind the glass, embedded in the glass. So the birds know that this is not air, this is an obstruction, and they don't fly into it. But also, where we didn't use the frit, he advised us to use an irregular glazing pattern. And therefore, that helps the birds recognize that it's not clear air they're flying into, but there is something there and they don't fly into it. Well, this has been extended. We learned a lot from that, but I think students in Swarthmore continue to learn from this because one of the experiments that they've continued in Swarthmore since the building was built was putting sensors on the windows. You can see the sensor up there on the fritted glass. They're called thump sensors because they detect when a bird thumps into the window. And they have them in this building, but they also have them in other buildings on campus. And they have monitored the number of thumps that the buildings receive. And I'm happy to report that the preliminary results from what I've heard are that the building where we took precautions to avoid bird impact have had, although they have had impacts, they've had fewer than the buildings where such precautions were not taken. So I think this is an interesting piece of environmental information that's often ignored by building designers. And sorry, this is just that same irregular pattern that you can see with the fritted glass at high up and the irregular pattern throughout. Moving on, another science building in Hamilton College in upstate New York. Here the green agenda was again different. It was driven by the Board of Trustees. We started with the existing science building that needed to be reshaped, reformed. It wasn't serving the needs of modern science. And it was forbidding and people didn't like it. And it was obviously needed the normal upgrades that buildings always need at this level of age. We proposed to the board that we consider LEED certification. They were a little cautious, but they did want to make a green move in the building. So what they decided was, this is part of a very big complex, so the existing building is just this piece in the front. What they decided was that the atrium, this piece, or that little red piece there, would become an energy showcase. And, oops. What we did was design. I'm sorry, I'm going all over the place here. What we did was we designed this atrium, which was inserted between the gables of the existing building. Designed this to be an energy showcase, and I'll just talk very briefly about pieces of it here. First of all, a big solar peak to keep out the summer sun. It is south-facing. And inside, there's a double curtain wall here. From here up, the double curtain wall with the space between the two walls. This is used in the summer for gathering the solar gain heat and bringing it up and exhausting it. And in winter, to gather this heat gain from the sun and recirculating it through the building. But perhaps interestingly, at the end of there's a energy kiosk. You can see a picture of it here at the end of the atrium that explains the way the atrium works. But it also explains the energy the building is using and does all those same things that Todd was talking about recording. Now the feedback on this is that this little feature in the corner of the building is interesting for visitors who press the buttons a little bit and look at it. Students mostly ignore it. They maybe look at it once or twice and it's not incorporated into any curriculum. And so I think, again, it's something to talk about the discussion, the usefulness of these kind of techniques. However, this building has had a very interesting impact in Hamilton in that the administration and the Board of Trustees have realized the importance of environmental considerations in design of buildings. And although this building wasn't LEED certified, the 3 buildings they have built since then have been LEED certified. So it has been helping not just educating students, but educating all of us in the importance of these considerations. Also, Hamilton has recently installed another kind of energy dashboard. This one is by Lucid Design Group, and you can actually go online. I'll give you the reference afterwards if you want to see it. You can go online. I did it myself yesterday. And a number of colleges have installed this particular kind of building dashboard, and it measures electricity use, water use, natural gas. If there are renewables, it'll tell you the contribution renewables are making towards the energy consumption of the building. And I think all of these kinds of techniques are important things for us in the future to help everybody have access to the kind of information you need in order to understand the impact you're making if you do make reductions or changes in how you use energy. I want to move quickly into the last project, which is at Trinity University in San Antonio, Texas. Now, this is a very different story. This is a story about a regional environmental characteristics. San Antonio is in, of course, the south, and it's in dry desert country, but it owes its existence to the existence of springs that are fed by the Edwards Aquifer. The Edwards Aquifer is a large aquifer under about 15 counties of south central Texas, which is used for artesian wells and for providing that part of Texas with water. Now, we all know how important water is in the survival of human life on Earth and indeed all life on Earth. But the aquifer is in limestone caves, limestone deposits all through that area of Texas. Now, limestone, of course, is a carbon sink created by organic matter that's become solidified. And so we thought that here in San Antonio, there was a big opportunity in this new building we were designing for Trinity University to think about these big regional things, the importance of water, the importance of limestone, and incorporate that into the building, particularly because Trinity's campus is actually on an old limestone quarry. So we were inspired by some of the missions of San Antonio, which have these interesting limestone walls and with arches in them, which reminded us very much of the famous Pont du Gard, the Roman aqueduct in Nîmes in the south of France, which you see on the left. And we sort of said, how can we incorporate this big learning lesson about regional environmental considerations into the design of this new science building? And so this building is going to start construction this year. So these are some schematic diagrams, conceptual diagrams. It did involve, just like the others, reforming of some existing science buildings and linking them together. And we said, what about running an aqueduct all the way through, made of limestone, all the way through to form that social space that connects the whole thing together? And what about making it an essential part of the entire building? So here it is. This is the sort of takeoff on the aqueduct. It's a big limestone wall that runs the entire length of that link that links all these buildings together. There'll be laboratories and classrooms opening off it. It has bridges on several levels so that you can see into the activities. And also there'll be an opportunity for each of the different science disciplines to have a display showing how their particular discipline relates to water or relates to limestone or both. For instance, the biology department could have a display of fossils. They could explain the formation of limestone. The geology department obviously could do something else. The physics department could have something to do with hydrology and so on. So this is still unbuilt and we don't know what the lesson is, but I think it's an interesting approach because here we're not talking about individual uses of energy. We're talking about some big environmental learnings that can be incorporated into the very fabric of the building. So that is a quick tour of 4 different science buildings, and thanks for your interest. I have some references, and you don't need to write all this down. If anyone wants to get any of this information afterwards, I have some handouts I can give to anyone who wants them, or you can give me my business card and I can email it to you. Thank you. Oh, sorry.
Sorry. Thank you, Carl. That was fabulous. We're going to have another 5th science building. Our next 2 speakers come from the firm Bolin Sawinski Jackson. They've come up from Pittsburgh to work on Ford Hall and to speak to us tonight. So we're very privileged to have them. The first is Natalie Gentile. Is that?
Gentile.
Gentile. Sorry. If I'd said it the other way, it would have been wrong.
That sounds more beautiful that
Well, I'm always for beauty. All right. In her 26 years at Bolin Sawinski Jackson, Ms. Gentile has been involved in a variety of projects, most associated with academic institutions. She's currently project manager for the $90 million Life Sciences building at Dartmouth College. Through a focused effort on integrated design strategies and multiple sustainability metrics, the building is expected to be one of the most energy-efficient life science buildings in the United States. It's not a competition over there, though. We have to don't get the gloves out. No. Prior to this commission, she was the project manager for the $60 million engineering and molecular science building at Smith College. Natalie's work in the area of sustainable design has been recognized with several awards. The Bear Run Visitors Center at Falling Water has been recognized as one of the top 10 green projects of 2005 by the National AIA. And CMU's new House Residence Hall has received the Commonwealth of Pennsylvania's Governor Award for Environmental Excellence. Both projects have received Silver LEED certification. And with her tonight is Rob Almer, also from Bolin Sawinski Jackson. He's been practicing for 15 years and has served as project architect on the Rensselaer Polytechnic Institute Biotechnology and Interdisciplinary Studies Building, and most recently held a pivotal role as project architect from its conception through construction of the $60 million Ford Hall at Smith College, which is projected to be LEED certified silver, and of course is here in the exhibition. So,
I will start. Thank you very much. Well, Rob and I are thrilled to be here tonight to talk to you about Ford Hall. We are going to focus just on one project. I don't know how we did that. So let me just start by saying, at Bowen Swinsky Jackson, we really love thinking about actually sustainability and how the buildings relate to the environment, how they are both good for people and for our natural resources. And we love working on college campuses for one very big reason. Campuses build lifetime buildings. Buildings are to last, and for those of you involved in college campuses and you live and work on them, you know that most buildings are around at least 100 years, maybe 200 years in some cases, particularly in this part of the country, and they should last, and they should be able to be flexible enough to adapt to future uses, and that's why I liked seeing the additions that were being done to these buildings, with very little demolition of the entire building. So, looking at issues of flexibility, looking at issues of quality materials, but mostly looking at buildings that people love and that they can maintain. So we think a very sustainable idea is making buildings that last, so people don't feel that a building is going to outlive its usefulness after 30 or 40 years and end up back in the landfill. So good sustainable idea, buildings that really last. But mostly buildings are for people. So we like to think that we build wonderful places for people to live and to work in. Some shots of the Great Hall atrium at Smith. So two things we're going to, or a couple things Rob and I are going to talk about tonight. First of all, how do you get started to think about sustainability? If you know this is really going to be an important goal for your project, how do you start? So we'll talk about that. And then we're going to just highlight two actual sustainable strategies that were implemented at Smith. So if you know anything about the Smith campus, some of you probably have been there, really set up along the lawn concept, not some of the more quad or orthogonal kind of arrangements that you see on campuses, but on the lawns. So when we were asked to design a new building extending campus southward, it really made sense to extend that lawn concept, that issue of green, and actually placing buildings with their entrances on the lawn, on the green space. Well, you will see it if you've been down there, that green has not formulated yet, but may in the future. But in the meantime, you know, inserting a building that houses science into a campus takes some good thought and some sustainable strategies in terms of smart growth principles about placing them where you get the highest and best use of your land. So how to start on a sustainable project? Well, what we suggest is a sustainability charrette. And what we would like to do is to do that off campus. Let's get all the important stakeholders to a neutral site so that we can really focus and really think hard and throw out all of the ideas into a lot of good brainstorming about what the possibilities are for a sustainable building. So we went to the Center for Building Performance at Carnegie Mellon University, headed by Vivian Loftus, who was our leader for this charrette. Vivian herself is really a researcher in the forefront of good workplace design and sustainability. So we met in their facility that BCJ helped design, the Center for Building Performance. And we brought along the architects, we brought along our mechanical engineers, our site designers, landscape architects, and the client, folks from Smith there as well, to just brainstorm a lot of really good ideas. Oops. Okay. So, what did we think about and talk about for a whole day? We threw out a lot of things, a lot of maybe crazy ideas, a lot of ideas that were good ideas at the time, but maybe we knew we couldn't implement them. But focusing on the ideas of light, of air, of, oops, wrong, see, this is using someone else's pointer. Okay. Thermal issues. You know, we talked earlier about really creating buildings now with good what we call envelopes or skins, your walls, so how you can really work to insulate buildings well so that you have less demand on your heating and cooling systems. And we also thought about what are some good things that this building should just do, and one of them, of course, was respond to the LEED scorecard, and I know out in the exhibit area there's some good explanation on the LEED system if you're not familiar with it. But I will say that Smith asked us to help them achieve silver certification. And that is not unusual for us at all, for a client to be asking that. It's wonderful that campuses are so aware of the LEED scorecard. But as we really took a look at the building in terms of energy management and electricity use and water reuse, and if you really focus on a lot of good green principles and strategies, you will find that the LEED scorecard tends to take care of itself in the sense that you really are building a lot of credits and points just by doing some good sustainable practices. Right now, we've just turned in our submission to USGBC. We are really on track for gold certification. And we're finding that that's really not so unusual that for someone to really be asking us to target toward basic certification or silver certification, and we're able to really exceed our expectations by very early on, these charrettes, thinking through really good green strategies and an integration of mechanical systems with the architecture, with the way the building might be used in the program ideas. So again, going back to the charrettes, thinking about important strategies and integrated strategies. So I like to show this slide because it's a little bit how architects think after you come out of a charrette like that. So we've spent a whole day talking to the client and writing on boards, and we go back to the office and we do drawings like this. But what it says to us is if you can start to see the beginnings of a floor plan there with rooms and circulation, and we're thinking, light and green spaces and sunlight coming in and, all these opportunities for solar or photovoltaic panels. So right away, we're all excited about how these ideas are going to be manifested in the architecture. And again, now we're stepping a little ahead in the game. We're still thinking about our sustainable strategies, but we're now looking at what's starting to become a building. So again, where's those big points where the light is coming in? Where are those important people places? Where are people going to gather? Where are we thinking about our planted roofs, if we want to do that? Our landscaping and green spaces, trees, where are we going to house all that good important mechanical equipment, heat recovery systems, whatever we might have that are going on to these buildings. And then an elevation really representing pretty close to the final attributes of the building. So Rob's going to talk a little bit about the importance of our big windows. Some opportunities here we're hoping someday still, if anyone has some extra money they would like to donate, we're still looking at, we have a nice place for some solar thermal arrays or photovoltaic arrays. We're all set to go. So if you're looking for an opportunity, there's a really good one down at Fort Hall. Okay, so so much of the sustainable strategies and systems that you put into a building, unfortunately, you can't always see them. They're in mechanical rooms, they're in the walls, they're in the insulation, they're in the kind of glass that you select. They're in, as I said, in heat recovery systems and a lot of other mechanical systems that we put into the building to save energy. But there are a couple that are visible, and Rob will spend a few minutes talking about that. One that we have at Smith really would be the way we manage our water systems, and the other is really how we manage our daylight and lighting systems.
Thanks. So the early soils reports for the project, well before this thing was ever even put to paper, we found that we had an enormous amount of groundwater. And because this building's sitting in this basically this bathtub of water, we needed to manage that. So not unlike most foundations where you have a perimeter foundation drain, but we needed to take this water and we needed to collect it somewhere. Coupled with the fact that we've now placed a 35,000 square foot footprint on this site, we had to address an enormous amount of rainwater collection. The building essentially, we're looking at a site plan here obviously. Smith's campus is to the north, which is to the left of our slide here. The mechanical system was framed on a penthouse element, all interior enclosed space, small enough to be contained and technically be classified as a penthouse, which is important for our heights that we're dealing with. the context of the building fitting into Smith Campus, the kind of apex or peaked penthouse roof was a definite intention in trying to reflect to some of the Victorian architecture existing on Smith Campus. In fact, as close as directly across the road. And of course, dealing with building heights, keeping our building low enough at its parapet heights, really set us up for some very low, shallow shoulders on either side of this penthouse, which were actually just perfect for a green roof application. It's approximately 15,000 square feet of actual membrane laid down, and then a fraction of that is ballast roof, and another great portion is low planted sedums. On the third floor, there's a seasons room directly off of our great hall space, which is a central core circulation zone. And that terrace is accessible by the public and has a much more extensive plant palette in it. You'll see some photographs of that later. But the issue with the green roof, and I mentioned this, the groundwater, excess groundwater, was that trying to collect all of this stuff and deposit it back into the city municipal system was too great. We couldn't afford to do that. So one way to mitigate that is with the green roof. After detention within the green roof system, absorption by the plant life, and just general evaporation, it reduced a significant amount of the rainwater runoff load to the city system. So, but investing or convincing Smith of investing in what I believe is their first green roof system, and not to mention 15,000 square feet of it, for a roof that was going to last them for the next 50 years was not an easy thing to do. They had their reservations. So we prepared a white paper for them, walking them through our experience, projects that we've installed green roofs in, as well as just the basics of where municipal system. While it's sitting in this tank, it gets pumped into a filtration system and then stored in a 5,000-gallon storage tank, which is what you see here just prior to being backfilled. This is a side view of one of the foundations being poured in the 30,000-gallon tank that sits underground in the green space in the front lawn of the site. So where was I? So it comes from the 30,000-gallon tank, comes through a filtration system, sits in this 5,000-gallon tank, and then as needed gets run through a booster pump system and fed back through toilets, urinals, and lab sinks, most importantly. And so all of the lab sinks are labeled as industrial water, technically non-potable. The groundwater source at the time, as it's collected around the building, is basically well water grade. So it technically is drinkable. And there's probably a good qualifying statement here in the sense that this is a fabulous idea, and it's an enormous savings of water, projected at somewhere in the 40 to 45% water savings of what the building would normally use. But they are having issues with it. Just recently visiting today, there are certain levels of lead and sodium and some copper that are of some concerns to the users. It's not, I think from an engineering standpoint, people will say that the water is safe, but it's still discolored, and that's not a comfortable thing for people to get used to, maybe in particularly in a lab. So we're working through that. We're trying to find the source. It turns out that the 30,000-gallon storage tank, which is actually collecting the water from the ground and from the roof, is actually exactly as we anticipated, actually cleaner than what's actually making it into the lab sinks. So there's some point between the storage tank, this 5,000-gallon tank, and the actual end user. Something's happening there. So we're in the process of working through that. So this piping system, as it comes into the building, this gorgeous mechanical space, is all painted purple, namely because it's a code mandate. So future renovations, people coming into the building and facilities, they don't inadvertently tap into the wrong pipe when they're hooking up a water fountain. But it is a nice map of the building as you're living in the space. It comes up through the mechanical system, and occasionally throughout the building, and in particular labs where there are no ceilings. I took this photo this morning. It's particularly poor. But you can see how it comes down the main trunk of a corridor and then drops down and jumps into your particular building. And in cases where, in a room like this, you can actually see it dropping down into a utility chase, to a tap that you can hook up, actually is what you're seeing right here, hook up your experiment to. A nice teaching tool. So the next is a bit more on daylighting. Here's a more clear plan of the space. Like I said, it's 35,000 square foot footprint, roughly 142,000 square feet in total. The building spans almost 330 feet in length. And as Natalie was pointing out in the earlier slides about the future expansion of Smith Quad, there's a very intentional purpose why the front entrance is placed so far off of Green Street, about midpoint of the building. One, it's just a bit easier to enter the building at the midpoint, and you're circulating south to the wet lab spaces, north to the dry lab spaces, and then this common element acts as your vertical circulation, as well as a core location for elevators and other common spaces. The terrace, case study room, loading dock is on the ground level. But unlike the earlier presentations, we're dealing here with a new building. So we have the luxury of maximizing our floor-to-floor heights, roughly 15.5 feet. That makes for an enormous building, especially something on Smith's campus. But in order to scale the building down, ironically, I think it's effective by making the windows more appropriately scaled to the elevation, which actually equates to quite enormous windows. Some of these labs have 8-foot by 10-foot tall windows in each of them, on average. So the south exposure of the building, let me just go back to the plan here quickly. South being to the right, and a very intentional purpose in the daylighting strategies was to start to spall out these walls and to maximize the daylight into the offices, into the corridor, and stairwells for that matter. So here's a view of that particular corner. You can see the Great Hall in the distance on the east side, and then these walls spalling out. The sun here probably something like 3 or 4 o'clock in the afternoon. So a cross-section through that Great Hall space. Again, that main entrance, this large vertical circulation, poured-in-place concrete stair, some balcony edges that reach out into that Great Hall space. And then all of these common elements. So this terrace space and seasons room, the case study room, and then more back of house, but yet common as far as the delivery methodology, common centrally located into the space in the loading dock. Some photos just illustrating this daylight. Let's see. These were taken actually just this morning. So even on a late March morning, something like 10 o'clock, there's actually some very nice daylight that comes in there. And so we're capturing the daylight in the early morning as you enter the building in the Great Hall space, and then again in the evening as you're leaving the space, the sun is coming back in through that seasons room terrace on the west side. So interior, some of the lab spaces. We, again, as early as, and it's hard to imagine, but we interviewed for this job in December of 2002, and the project just recently opened in January. So this is a better part of 7 years, as most lab projects go. But it's older than 2 of my children. So. But it was back in 2004 when we had the sustainability charrette, bringing our lighting consultants on board, talking about strategies for lighting of the lab spaces, very intentionally locating these right over the edge of the lab benches to maximize the light levels both on and off the bench top, minimizing shadows that are cast by the users, and of course then maximizing this daylighting. Teaching lab, this is a typical teaching wall. All of the core spaces are obviously inboard off of the perimeter, allowing to maximize daylight. Where possible, these are actually open spaces, this is a very nice lab, nice clean lab before the users have moved in. And then let's see. So again, presentation lighting and projection screens dropping down on the front of the classroom, and then natural daylight coming back from the rear. So here's a great example of the daylight dimming system that's actually been executed at Smith. The outer two 4-foot light fixtures are on a daylight dimming control. It's a very simple mechanism that gets mounted into the light fixture itself. So when you have this flood of daylight coming into the space, as is often, these lights will drop their light levels. So maintaining a constant foot candle in the lab, whatever that might be preset to, and then where partitions were absolutely needed for privacy or security, we try to maximize the interior windows or lights in between labs or from labs into core spaces to let that daylight fall as deep into the space as possible. So it's two very simple credits, but maybe overlooked at times for LEED is light distribution into the space and then actual daylight views from the space to the outside, and certain percentages of the actual occupied square footage. So each of the labs is, instead of your traditional solid frame entrance door, we created a storefront for each of these labs. Again, trying to increase the interdisciplinary, making all the labs a bit more inviting and friendly, not just such a mystery of whatever's happening behind that door. And it's always a tough thing for architects, because I think that one thing you could see, although having walked through the building, I think the Smith users have actually embraced it. But one thing you could see is a lot of people just taping up these windows because they don't want that kind of exposure. But it actually is working. They seem to actually be embracing it. So you can see the daylighting coming in, and then this being one of these core spaces where, again, we've just tried to maximize the amount of light or glass to let that light come in from the lab into these core spaces. And a lot of these core spaces don't want natural light, dark rooms, environmental rooms, and things like that. So those are obviously intentionally put into the central core. And then just a few more great photographs that I'm particularly fond of. But just for context, this is the north elevation, stacked meeting rooms on each floor. This is the north dry lab. Here's the case study room that kind of sticks out and flanks out, allowing daylight views back to the campus, and then that seasons room terrace above it.
I have a question on, which you can answer later, but these slides highlighted, these very tall windows, the top third of those windows seem to go up into a
They do.
field above the full ceiling.
They do, and you can see the shadow actually of what's happening there. This is just spandrel glass, so we've intentionally enlarged the window and dropped it almost to the floor level. But it's spandrel because typically along that perimeter you have casework and the like.
I'm talking about above.
Yes, and above, likewise, just trying to maximize the daylight, but trying to maintain a ceiling that, when needed, obscures the mechanical systems above. But it's set back off the window. It's set back 2 or 3 feet off the window. So the daylight can drop deep into the space. You can't visually see through those. If I can go back to the...
I'll ask you later, but I'm
Sure.
curious as to the value of that top third of the
So you can
glass.
see,
Whether
yeah, there's actually another foot or so of glass that's above that.
And if you did daylight studies without that versus with it, just as Todd was showing that he got 1,000% return on his shower heads,
Mhm.
I'm wondering what the return on that top third of the glass is.
As far as
I
it-
suspect it's not very great, or probably not.
I agree. No, I agree. I agree. So that's the end.
Okay, our last speaker tonight is Tom Davies. Tom is the Director of Design and Construction for Amherst College, In his 10-plus years there, he's overseen over $250 million worth of projects,
Can you believe that?
including renovations, new construction, infrastructure, and a cogeneration plant. Tom's background includes consulting, architecture, construction management, and engineering. He holds degrees from UPenn and MIT and is a licensed architect. So without further ado, are you ready?
I'm ready.
Okay.
I am. I'm actually going to sit here
Sit there? Okay.
and talk to you all. Thanks. Anybody want to like just stretch for a minute? It's been a long time hanging out here. Thanks. Well, thanks. So in thinking about this, I thought, well, geez, I'm going to be presenting here, and I'm going to be talking to experts. I can see some of your faces out there. What can I say? And what can I add to this? We got experts up here talking about, fantastic advances in green architecture, and so I'm going to give it a shot. What I'm not going to do, probably the safest thing would be like Amherst College is doing all this incredible stuff. I'm not going to do that. Amherst College has a terrific PR organization, and they get terrific PR, and this may, I won't go any further. So anyway, what can I do that might make a difference here? Because this is something that is just so important to me, and I suspect to all of you, since you're here, and should certainly be really important to everybody else who's not here. What my objectives are for the next 15 minutes, I say optimistically. Share a few successes of things that might work in your project, successes that I think might be kind of interesting, clever, obviously not PVs, because you know all about that. And maybe engender some incremental learning. And be real, be honest. How much does this really matter, given the context of what's happening around us? What's the value to this? And if it has value, certainly it has value. We've been learning all kinds of things, but is it enough? And maybe there's something beyond that, and it does get to the bottom line there, something that I've been thinking about, which is the potential of the campus being this little government that could, because our big government isn't doing it. The Maldives is doing it. Other governments are doing it, but our government is not doing it. So maybe there's something in that. I don't know. This is an exploration, and we can talk about it afterwards if you like. So let's all take a deep breath, because now I'm going to say things that aren't very pretty. The context of all of this, really troubling, a really troubling context. We're talking about energy efficiency and doing things better and making improvements. But it's pretty grim, really, when you think about it. And the more you know, the more grim it is. The fog of green, my first comment here, is that, there's obfuscation going on at a monumental scale around the world in this country on every level. I was reading something with my wife last night that reading about a book called Green Ink. I don't know if anybody's read that. Talking about how the major environmental organizations, nonprofits of our country, are completely corrupted. They've been bought and sold. And so, it's no wonder that 10% fewer Americans, there's a fog that is very dense. The second aspect here, money talks, and not so much in the what you might think I'm talking about here, but unfortunately, we're not running out of fossil fuels soon enough. They're still really cheap, right? And they're going to stay really cheap, it looks like, long beyond when the tipping point happens. And that's too bad. Maybe that's a little defense mechanism that our Earth has or something. I don't know. But money talks, and stuff's not happening, right? And the third piece is that nature is apathetic. It doesn't care what is feasible political legislation or what is not. Nature's doing what it's going to do. Okay, so that's heavy. So we got some successes. So lighten it up here. I totally cribbed this from Todd, by the way. We did a talk on cogeneration a couple years ago. So a few successes. The first one, it just blows everything else out of the water. We put in a cogeneration plant. 30% reduction in greenhouse emissions from Amherst College. Wow, great. Give me some more of those. Where can we find the next 30%? There aren't other 30% like this. Yeah, do it a couple more times and you're done, right? That'd be nice. So, if you don't know, Todd said earlier, this simply involves not throwing away a tremendous amount of energy. That's a pretty smart thing to do. It's right here. It's happening. These lights and the heat and everything. And UMass put in a huge cogeneration plant, which is running now. So isn't that wonderful? We can pat ourselves on the back. But did we do this because we wanted to lower greenhouse emissions? We'll say that sometimes, but really no. Right? UMass didn't do it for that reason either. Did it because it makes financial sense. So, but it's a good thing. Another thing that we've been doing is adaptive reuse and salvage of buildings. That's a great thing. Todd mentioned that earlier. This is a building that has gone through many different lives. Talk about it a little bit. But, again, is this something that, this is fun. This was one of the first gymnasiums in any college in the country. And actually, this was a pioneering notion that physical fitness, enabled you to be smarter, and to learn things better. This is totally pioneering. And so, notice the diversity. But maybe, there can be this kind of pioneering again. So here's the building way back when it was a gym. Then it became, everybody knows, the Pratt Museum. Now it's a dormitory. Yes, this is a first-year dormitory. Wow. I'm still getting over that, yeah. This was not my idea. I want everyone to know that. Using the building over was, but this is a little bit extravagant. So, did we do this adaptive reuse because it's, a green thing to do? No, we did it because history is really important at a place like Amherst College. So here's Charles Pratt, what we've been looking at. And look at all these wonderful things, yeah, it's a blocking free. We did all these great things. We salvaged stone, blah, 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 blah. What's that one? No AC. So that's point number 3. We don't air condition our dormitories. It makes a huge difference. It's New England. We don't have to. They're not here in the summer. So some people are here in the summer, and they rent the spaces, and they do all kinds of summer programs and whatnot. So we did a little study when we started the residential master plan about 10 years ago, and found out that the market is basically inelastic. And the rental that we could charge for air-conditioned dorms was fractionally more than non-air-conditioned dorms. So forget it. Decision was taken. Thankfully, we have not air-conditioned any dormitories. You might say, oops, hey, what about that big wall of glass facing southwest on these dorms, Tom? There's a little secret out back just for those spaces. Sorry, don't tell anybody. The students don't know that those are dorms. But yeah, I'll quickly move on. Right? So the next thing that we've been really getting into in the last couple of years is focusing on the envelope. There are experts here that know much more about this than I do, but I'm learning, and it's really an important thing to know a lot about. If you haven't been to talks by folks like this guy sitting here and other experts out there at Nessie or the other.
Virus database has been updated.
Who knew? Wow, that's good. We'll look at that later. That was really good. So yeah, building envelopes is not really exciting, I guess, as much as that. But really getting into this and learning a lot about it and bringing a lot of focus to it, holding our consultants' feet to the fire, and this is what makes the difference. It can make an enormous difference. Air barriers. And if anybody hasn't done this on their home, call up Wamiko and make an appointment and get CET to come over and do an analysis, and they'll fix things for you and save you money. But it's the same kind of thing, focusing on the envelope. We've been working with one particular consultant, and he's been amenable to dropping by for an hour when he's in town and looking at some drawings. It's been terrific. So we've really been focusing on that, doing all kinds of things with, foam insulation, and when we come across weird black stuff in the back of a wall, wondering, oh, geez, can we insulate that, or is it going to create a vapor barrier situation that's going to make the wall disintegrate from the inside out? And kind of, figuring these things out and moving along. The next thing, a little thing to share is good old Puritan pragmatism. Stuff, stuff that's always worked. This was an entry to a renovation for an office building, small office building that we were just finished up about a year ago, and the side door, the one that actually everybody would walk into, didn't have a vestibule. So we added a vestibule there, that kind of thing, things that work. This was a nice little thing that one of the folks I work with came up. We don't need to heat the attic to 70 degrees, We could heat the attic to 50 degrees. And so we figured out how much insulation to put into the attic floor to enable, just passive heat to spill up through that and keep the attic warm. And, we don't know. We think it's working. We think it's probably saving some energy there, but it's working. We talked all about these shower heads. I put, in the talks that I do on this, I actually put the model number there because people are always asking afterwards, what are those shower heads? And by the way, get 2 for your house. We have at our house, it's terrific. It's like, what is it, 1.25 gallons a minute or something? It's great, and it feels great. Nobody's ever complained about this. And, for students not to complain about something, they still take 15-minute showers, but, it's 1.25 gallons at a time, at a minute. So that works really well. Other successes, and here's where I start to wonder, we're building awareness. Are we? Or are we just kind of greenwashing? This is a building that's right up at the center of town. It's very prominent. We stuck we said, okay, it's historic, but we're going to put these solar thermal panels up there. It generates a small fraction, maybe 10, 15% of the load for the building. And does it change any habits? I guess it's a good question. In fact, it might change habits in the wrong direction. People might think, hey, it's free hot water. I'll take a longer shower. I don't know. I kind of wonder about that type of thing. But what we've been able to avoid is this kind of stuff. If you go into Google Images and do a search for green architecture or LEED architecture, you get things like this. This is in Abu Dhabi. This is a LEED gold building. It's in the desert. It's a glass building in the desert, people. Okay? So are we worried about daylighting? Do we think that these are common spaces along the exteriors? And it was LEED certified green, all that kind of good stuff. So, so we're avoiding that. That's good. And we're actually not following the whole LEED thing. I'll talk about this very briefly. Todd mentioned that over at Mount Holyoke, the energy modeling actually predicted what actually happened. That's incredibly unusual. Some of you might be aware of this, that there was a study done a year and a half ago or so, and it's kind of a scatter diagram. This is kind of mapping what was supposed to happen with LEED certified buildings with what actually did happen, and it's all over the place. And in fact, the ones underneath the line there, it says, they're using a lot more energy than even the baseline, much less what is supposed to happen. So something's not quite right there. I kind of took this information and said, I wonder what the bell curve looks like for that. And so the kind of fuzzy blue there is maybe, what a bell curve kind of should look like. And I took this mini course when I was in grad school over a J-term on statistics and statistical analysis, and they taught me that this is statistically irrelevant. That I know. I don't know. Statistics was hard. I didn't really learn all that much. But I know that this means nothing. It means there's absolutely no relevance between what's modeled and what buildings are supposed to do and what they actually do afterwards. And there's all kinds of reasons people think that might be the case. But that's a problem. And it certainly adds to this fog of green. What's happening? Can we really feel good about this stuff? So. All right, so next topic. There's more to that, right? But next topic is Follow the money. So it just so happens that a lot of campuses aren't really building very much right now. So we've been able to focus on some other things. So when you think about it, the new snazzy green construction, right, optimistically, maybe that's 20% of the gross square footage on the campus. It's not, it's less than that. But say they use like half of the energy per gross square foot of the older buildings, which is terrific, right? That's 10% savings. Yay, we can all be excited about that. But it means that 90% of the building energy use is these older buildings that really aren't going to be renovated anytime soon. They're not going to be LEED certified. They're not going to be torn down and rebuilt and other things take their place. They're going to be there, as we've heard, for a long time, right? Buildings last a long time on campuses. So that's a good place to focus. And we've been focusing and actually working with Todd and coming up with all kinds of great things to go after. We've put together a long list of just brainstorming ideas, low-hanging fruit. It might be inefficient lighting. Here's some. Any light that's hot, you know, that you have to air condition the space because the lights are on, that's a bad sign. And all kinds of different things. And at a big campus like this, or Amherst, or any of the campuses around, there's all kinds of opportunity. So in that 90%. So we've been working on that and moving along and working through those things. And, you know, so here's a typical building. Well, you know, you look at this building, right off the bat, it's like, okay, they're triple tracks, and most of them aren't closed. So we could close the windows. You know, that's a good low-hanging fruit. We could insulate. You know, there's not much insulation here. And, you know, this building's not going to get renovated soon. So, you know, these wonderful, this is one of my favorite buildings on campus, but, you know, these 1960s buildings, good question. I don't know. You know, there are no triple tracks that fit that. And, you know, it's single pane, steel, mullion, and I'm not quite sure how we're going to improve this one. No, it's not going to fit that. Here's a fun one, just for ideas' sake. You know, I walk by this building pretty often going to a job site, and I noticed that, you know, it's sporadically used. It's a kind of a function house, a function room, and it's used for meetings and, you know, things like that. And there's always a little cloud coming out of the smokestack, pretty much all the time. I'm like, what's going on with that? And it turns out we started looking at it and poking around. I'm like, there's something going on with that building. Sure enough, it's a big one-story flat pancake, essentially, and there's no insulation. There's no insulation in the roof, you know, or a little. There's basically none. So the heating system has to run all the time. So when we talked about this with the guy who runs the mechanical shop, he said, oh, that'd be great if you insulated that building, because then we could set back the thermostat. Because we can't set it back because it never comes back again. It has to run flat out all the time, all winter long, so the people who use it on Friday afternoon are warm. So, you know, so there's an idea. We could go after that kind of thing. This is our gym. There's 1 inch of insulation in the roof in some places. There's lighting that we're working on. There's all kinds of things there. We started poking around there. We found out that there are there are dampers, basically open to the outside, louvers that you can see daylight through, right from in the space. So, you know, there's great opportunity that's not the schnazzy stuff that, you know, is all around outside there. And that's really, I think, what we're starting to really focus on. All this other stuff, I'm not saying the other stuff isn't really important. It clearly is. We have to move the technology forward. But it's this dumb stuff. This is the little kitchenette next to my office. There's no water cooler there anymore. There was a little bubbler thingy that had been there for years and years and years. Now it's not there. Why? Because Amherst has good water. We don't need to get it from, you know, Poland, Maine, you know? What is that? And, yep, so stuff like that. But it's a little bit scattershot. This is a kind of a grassroots thing on our campus. This is in the admissions admissions office. They have a funky little filtering system, which is great. They even have their own little green group in admissions with its own newsletter. And they call up and they say, hey, we've got this idea, we want to do this, we want to do that. So there's, you know, there's this stuff happening around the campus, but it happens in little pockets. It's not universal. Right across the street in the gym, There's a very different sentiment. I won't share explicitly what I was told yesterday about the idea of turning off lights when people are not in a space. It was very explicit that the person that I was talking to had absolutely no interest in the idea of having the lights turn off when there are no people in the space. Very, very clear. I won't share. So anyway, I was going to, but I think it's probably best not to. What's that?
Is there a reason, that's like security or?
It's going to be awful if it's dark. It's bad enough as it is, and now you're going to make it dark, it's going to be really terrible. So not much team spirit there. And why? Why no team spirit? Because it's optional, right? I mean, saving energy is optional. We don't have to. It's a nice thing to do. So why? Because Amherst is in the United States of America, where saving energy is optional, right? So, we build these fabulous buildings, and, this is a great building. It's got an exterior insulation system. Everything's taped in. It's tight as a drum. It's got heat recovery systems, all this kind of great stuff. Shepley worked with us on this a few years back. But look closely, the windows are open. It was about 40 degrees this day.
Top story.
And this was, around the other side, this window was wide open. And the room inside is only like 150 square feet. So what's going on? Maybe we oversized the heating capacity? Is that possible? This was inside. I said, one of those is a common space. Are there people in there? No. Windows open. So, there's no kind of JFK kind of edict of like, ask not what your country can do for you. It's optional, right? Here's another good one. Green, window open, not green. So, and again, it was like 40 degrees this day.
So Tom, this is all, I guess, because there's no relation between stories. The air is moving up through the building.
Maybe, but there's not that. It's not like there's a big atrium or anything like that.
No.
And it happens on all levels of the building.
Or maybe just the controls on the heating system aren't quite doing the job.
No, everything's been commissioned.
It's always the top floor.
More likely than not, it's the top
Apartment
floor.
buildings, that's typically what happens. And the ground floors are freezing, the top floors are
Yeah,
freezing.
the stack effect, sure. Yeah. So, okay, well, this is great because, look, the faculty, they keep their windows closed. That's great. So the adults know better. That's nice to see. But, but not really. Oops. Again, it's optional. Kind of like driving. What do you drive? You can feel good about driving a smart car. Oh, right around the corner as I walked around here, I didn't take a picture because they're big guys. It looks kind of scary. There are 2 Escalades with diplomatic plates at the admissions office with big guys standing. I was like, I wasn't going to take their picture. I thought it would have been a good juxtaposition, though. So, and there are all kinds of great things we're trying to do. This is the entry to the cafeterias. The first thing you see as you walk in, okay, we're buying a bunch of local stuff, but it doesn't really translate when you go around to the snack shop in the other building run by the same people. It's like, oh, is high fructose corn syrup grown locally? I like the Cheerios good to go. So, again, it's optional. This is a good one. This is as you're leaving the cafeteria. I had to take a picture of this. Apparently, bringing your plates back is optional, too. So, why? Because this is the societal norm. This is where we are. Why would we expect it to be any different, right? Some places do, right? I mean, like University of Maryland, College Park. You walk onto that campus and something is different. They've created their own set of norms, right? It's not societal norm anymore. So this is what a campus can do. It can say, okay, we're not part of the United States society, we're part of the global society. Amherst College prides itself on being part of the globe and a very diverse place and bringing in, it's a needs-blind admission for international students now. It's like one of the only places in the country that does this. So let's be global citizens, right? Let's not be part of the norm for the United States. Let's be part of the norm for the world, which is quite a bit different, right? on average. You agree with that? So, what does that mean? Oh, this is one of the things in the philosophy statement of the college. To enlighten, care for, and advance society as a whole within and beyond our borders. So I take that as an opportunity to say, okay, this is what we should be doing. We should be supra-societal. We should be beyond society. What we can do as a campus, what all campuses can do. Make it not optional. It's not optional to save energy, to reduce carbon dioxide output. That's something that a campus can do. It has all of the ability to do that. It's like a little government unto itself. You know, the trustees can declare it, and it will be. It might take a couple of years, there might be some resistance, but it will be. We can stop greenwashing and feeling good when there's really not very much reason to feel good. You know, this happens on a fairly large scale at a lot of campuses. You know, we're getting a good story out there, it's good PR. You know, it's real, but how does it fit into the overall context? We can recognize the costs associated with what we're doing. You know, we are energy hogs. Campuses are energy hogs. There is no doubt about this. You know, we have a science complex at Amherst College that is 1964. It was built when energy was going to be too cheap to meter, and it performs as if energy is too cheap to meter. Now, we're in the process of getting going with a renovation for that, but, you know, it's just an emblem of the amount of energy that's consumed by these campuses. We could at least recognize the cost to start, and then we could actually increase the costs, because that's what the government of our country is not doing. You know, they could do that, but they're not doing that. But campuses could, and create incentives for reducing usage. And we could educate. Oh, my goodness, wait, we could educate. Campuses could educate. Yeah. So what should we educate? I think this stuff. You know, I think that it's incumbent upon everybody in these campuses and in our higher education system to really take this on, you know. Yeah. So it comes back to what can we do? So I'm not a trustee of a college. But what can I do? What I do know is that colleges really respond to their alum. And so is anybody an alum of a college? Yeah, a couple? Yeah. So you can contact where you went to school and say, hey, what are your green programs there? Are you really making a difference? Have you joined the President's climate commitment? Or, you know, things like that. Those will make a difference. I haven't done that, by the way. I just thought of it this afternoon. Anybody who's a parent of a student in college, I think, has a lot of clout in that regard as well, to be able to really call them out and make a difference. And if you work at a school, maybe there's a little bit of opportunity there. So what you can do, you can get on the bus. I love this picture. This is in Quebec. They use these things, right? It's only like the next country over. It's over there. It's not as far away as, like, you know, Pennsylvania or something. That's great. Get on the bus. So, or get on this bus and you know, and get loud. And I think that's really a pretty critical thing at this point, because it's serious. So that's what I had to say. Thank you.
Thank you, Tom. That was really wonderful. A wonderful note to end on, and the idea of bringing responsibility into it is larger responsibility than just the architects who are working tirelessly to help us in the right direction. So does anybody have any questions? We've gone on a long time, but there's been so many interesting things to cover. So, but we can open up to questions and discussion now for those of you who can stick it out. Anybody? I can pass the microphone.
I have a question about getting people to those buildings in a green way. what have their campuses done so far, what you could do more of. I realize there are small campuses that you've showcased and students can walk to them. But what about staff and all the people who come to the functions and events that are hosted nonstop on these campuses?
I can speak on for Smith. This is nothing to do with the design team by any means, but it was part of the program that, at least for Ford Hall, there's no increase in population. So although we've built this new 142,000 square foot facility, it was a decompression of existing space. So there is no increase of population and no real increase of student population. So it kind of click through everything very quickly. There's no parking on the site. There's no additional parking because all of the vehicles are already on campus. So it doesn't quite answer your question, but I think it is a unique aspect of this particular project that there was zero parking calculations. There was proof that we weren't increasing the population. The city was very concerned in that because they see this new building going up. They want to make sure we're managing that issue. And studies were done as far as transportation and different, no parking.
Can I add to that? Another thing Smith College does for their employees, for their full-time employees, not this part-time employee, is you can opt not to get a parking sticker, and they will pay you $400 a semester to take the bus or ride your bike. You get a few parking passes for inclement weather or emergencies, and they set you up with a Massachusetts rideshare program. But $400 is a pretty good motivator. But it's a lot cheaper than a parking space. What's a parking space cost? $12,000?
Oh, yeah,
To
a
build?
surface lot, yes.
Yeah. So parking a piece of tarmac to put your car on is $12,000, but it's really hard for these places to cross the threshold to actually pay somebody a few $100s not to use a space.
Sure they can hear you.
I enjoyed your talks. I was curious if any of you, there wasn't a lot of discussion about landscape and landscape water use, and I was curious if any of you are looking at projects or moving toward organic landscape practices, soils, no synthetic pesticides, and also irrigation-free lawns and landscapes. Is that something you can talk about?
Yeah, clearly thinking about the landscaping is really important from many aspects. I will go back to one of our very first lead projects was the, one project we didn't talk about tonight, but was the dormitory at Carnegie Mellon University where we actually put 50 new trees back on the site just to help with the microclimate, to make it a more pleasant environment to people to live in, and just to really bring some nature back around some dormitories, which in this particular case was really put on a pretty vacant site. They were all trees native to the Pittsburgh area, and they all are non-irrigated. We were doing that at Smith, we're doing that at Dartmouth, we're doing it in a number of our projects, looking again at natural landscaping. So these are plants native to the area, locally, drought tolerant, locally grown. Not just, for one reason, because you do get a LEED credit. You get a couple LEED credits now for not doing that. LEED does allow you to irrigate for the first year to make sure that you establish your planting, but you cannot put any really permanent underground irrigation systems in. So it is educating our clients. I think, again, the campuses are becoming very smart and aware that it saves them on maintenance, I would think, too, if you really are looking at plants that are self-sustainable over the change of seasons in a particular climate. For BCJ, we do a lot of work in Southern California, actually throughout the United States, and it is important to be working with local landscape architects, people knowledgeable about the plant materials and the soils and the climate conditions wherever we are building. So that's really important to us when we are putting together a project team. We like to have those consultants, our civil engineers, landscape architects, particularly local to the location of the project. Maybe the same way for you, Cal, because we really, they're the smartest ones to help us to be intelligent about materials, plant materials that are going to sustain itself. And even, the simplest thing about just the seeds that you put in the grass, really vary with climate. So it's not even trees and bushes and flowers, it's really even the grass seed that you pick and the soil that you put it in. Okay.
You'd be surprised how many campuses, I'm sure everyone's experienced it. I've experienced it almost on every campus, walking across it after 2 inches of rain just dropped the night before, or it's 20 degrees outside and the sprinkler systems are kicking full steam, watering that lawn. Because no one's monitoring the timer or the water level sensor or whatever. Something's going awry.
Question for Tom. In your slideshow, you showed towards the end a lot of windows open in cold days, and I drive by campuses all the time, and it drives you nuts. I was at UMass, and the sun was hitting just right, and windows were open. You could just see the heat flowing out of the building, and kills you. Did I notice in one of your buildings you now have controls, individual controls in the room, and it shuts the system off when the window's open?
Yeah.
And how is that system working?
Good question. We put that into Hitchcock, which is the one with the big array on the roof, not in the individual rooms, but in the common spaces. They have very large windows, and so we put sensors in, ties into the DDC system. Most of those spaces don't have DDC, so that's one obstacle. Basically what it does is it sets back the T-stat to 55 or something like that. So, you open the window and it's going to get cold. I guess just anecdotally, I'll say that those windows are not left open that often. Or I can't remember anyway walking by and seeing that open. I don't know that we've actually studied whether they're working. And, the other thing with that is that if you put that into a kid's room, they're not dummies. They'll overcome it pretty darn quickly. It doesn't take that much. There's a little magnetic switch. So, no, we haven't opted to do that on a wide scale.
It's a big challenge. Everybody likes their space a little bit different, as we prescribe.
It is. And one of the things I'm thinking about that is that, we tighten these buildings up so much. It may be that the answer is that we have to have heat recovery ventilation in each individual space, even if there's a window that opens or whatever, because, that's the only way to keep it fresh, particularly if you play hockey.
And there's an argument for the energy conservation side to the just employee productivity side. I think that the ability to open a window is a convenience that may be a bit overlooked. The north wing at Smith College has operable windows where the ventilation system allows for it. The wet side, the single pass air side is airtight for that reason, just because it's almost waste of energy. But there's something nice about being able to open the window and have that direct control of it. If you can get your mechanical systems to cooperate with you.
But some of it also is to change a little bit of how we think about the buildings. I mean, in some of the dorms, like in Mayo Smith, for example, there is an adjustable thermostat, but the thermostat does not go off. So even if that room is wide open, that room is still going to try and heat it to, say, 60 degrees, I think, is the minimum. Yep. And that student might want that cooler from that space. And for us to cross the threshold to say, let's allow that student to turn that room off, because we know, even if they leave that window open, we're not going to freeze the system in that room. Because it's not going to be all the windows open, it's going to be one room. And so it involves some thinking about, from us as architects and engineers, to say that's okay if we don't heat that one room and the windows open.
Thank you.
I have a question about passive solar design. It seems like the bigger the project gets, the more windows it has. And I understand the concern about daylighting, but you can save anywhere from 20 to 40% of the energy needed in a building with just passive solar design. Is this out of favor with green designers, or? So that's my question.
Yeah, I think there's a couple of things, I think. There's a couple of things that are go into this consideration. One is a lot of the buildings that we talked about, or certainly the buildings I talked about, have a lot of existing buildings there, which are what they are. Secondly, in science buildings particularly, frequently the envelope is not the critical thing, but when there's so much ventilation, it's the opportunities for heat recovery that you can do with the ventilation that's happening for safety reasons. And I suppose finally, the more complex a building is, the less easy it is to adapt passive solar design techniques. That's not an excuse, I think it's just a fact. But I agree with you that it is something that tends to be overlooked in bigger, more complex buildings.
Other projects, we are actually putting what I will call lids or brims on the tops of the building a bit. What that at least does is allow some shadowing of the top floors of a building. And they really are effective, and when you run the energy modeling, because none of us have talked about it, but all the buildings that are LEED certified have gone through energy modeling many times over on a project, actually. So we have found at least putting what we call a brims or a lid or different big cornices, whatever you might want to call it, or soffits on projects, at least helps shade those top levels. Obviously, we're not bringing them out far enough to shade the others, but it really does help, and the modeling is proving that as well. Also remember the glazing. Fortunately, the research on glass performance has just really helped us out tremendously. That industry has done a lot to really bring a glass to the aid of architects and energy managers and people paying the heating and cooling bills. So that's been terrific. I will say that projects we didn't show to you, we actually, in different climates, where we have particularly west-facing, we have employed some automated shading devices, not passive, but recognizing that particularly the west sun is hard to handle. So looking at automated systems, because on these large, tall buildings, passive strategies just aren't getting you everywhere. So looking at other automated techniques that shades will lower as the sun comes around a facade and gets very strong and intense.
Exactly. I mean, each direction of the building needs to be treated separately.
Oh, and I think, absolutely, and I think as you really look at the kinds of architecture that is represented here, every elevation is different and unique on every project because you're shadowed by other buildings, or for college campuses, we're given our sites. You can't pick your solar orientation, so to speak. For Ford Hall, clearly we were given a site that's required a north-south building, and there's no other way around it. And I think as you look at campus planning and you look at the campus master plans, and for architects, we just have to make the best of the sites we're given in terms of passive solar.
Anybody else? No? Yes?
Going back to accommodating people who choose to live a car-free lifestyle, is there any room in your design process to incorporate elements such as bike shelters that protect your bike, which is your mode of transport, from the element, or bike storage facilities within the activities of your new buildings or remodeling your old buildings? Or somehow encourage your faculty and staff to role model the life and getting on the bus for their students to educate them?
Well, LEED is a big help here. And in fact, I don't want to be, LEED, I said, is a big help here. Actually, I don't want to be cynical, but in the early days of LEED, it was almost a joke among architects that the easiest way to get LEED points was to put in a bike rack and a shower. And all of a sudden you had a couple of LEED points. And it was, compared with other things you had to do, it was a really easy thing to do. So I think LEED actually has helped everybody recognize the importance of providing for alternative means of transportation.
Another credit specifically references pedestrian distance of the site to the nearest public transportation, so say maybe a bus stop. So I think it's a half a mile or a quarter of a mile, I think. So if you just simply have to prove that distance, that travel distance, as you would walk it down the sidewalk around the corner to the left. There's the bus stop.
Our office at Amherst College, our building has, 20 people working in it? And on any given day, you'll find 6 bikes in the basement. And so we have people making decisions every day about how the campus will look, a significant number of which are riding to work. But what we've done is we've guerrilla commandeered indoor space for our bicycles. And so, you know, and at Smith, we were looking at some sheltered bike racks today. So the decision process there, but then again, like Tom says, money talks. You know, you know, look at the cost of the space per square foot that we store our bikes in. You know, it's a finished space. It's a finished indoor space that has a value that we've now taken up with our bicycles, and yet we lack the ability to say a $30,000 architecturally nice rack with a roof and sides and everything, that's too much money. We can't spend that money, but we can take over the space. So it's,
So we could spend $12,000 a parking space.
yes, or $30,000 for a parking garage. So it's not easy, but I like your comment of example. You know, showing people that it's possible. You know, taking that 5 college bus back and forth is a wonderful thing, and it works. You know, and also the different campuses have a very different culture on driving on campus. And one of the schools, people tend to drive on campus from meeting to meeting. But it's always fun to be the person on foot that beats them to the next meeting because they're looking for a parking space. So.
Anybody else? Thank you so much for coming.
All right. Do people want to
I don't know
delete
if
stuff?
you have your things still in, if you can just download them onto my computer or the VR for like free for speakers.
Mine's sitting on there.
Oh, yeah, yeah. Oh, definitely.